Hello folks, and welcome to this lesson on Hess's Law, Part 1. By the end of this lesson, you should be able to use various thermochemical information to solve Hess's Law problems. So before we go into what Hess's Law actually is, I want you to remember the fact that enthalpy is stoichiometric, and so you can take an equation and you can multiply it, say, by 2, and this will be true, or you could also reverse it and have this be true, and you could also not just take this one reaction, but you can take multiple of them and you can add them together. And while you're adding them, if you find that there are like terms on either side, you can cancel them out too. So what do I mean by that? Well, look at the equations that I have up here. Now, I've chosen these particular ones and I've done things to them in a specific way because I want to get a specific final equation. Now you may notice this first reaction looks like the combustion of butane, except I've reversed it, and so that's where this value is coming from. This one looks like the standard enthalpy of formation of carbon dioxide gas that I've multiplied by 4, hence that. And this one looks like the standard enthalpy of formation of water, except I I multiplied that by 5, in which case I get this. Now the particularly eagle-eyed of you will also notice that if we're looking at the enthalpy of combustion, this should actually be liquid, but let's leave things as is for now, and we're just going to continue on. So that just means that this value is a little bit wrong. But let's continue on and get to the point of this whole adding equations thing. So when we are adding all of these together, I could simply take all of these, write them all out, and then they will all become all of these. But notice that I am using carbon dioxide in this reaction and I'm producing it here. So overall, there's no actual carbon dioxide being used or produced. You can also see that I'm using water here and I'm making water here, so overall, nothing's happening with the water. Whatever is being used gets produced again. You'll also see that there's a whole bunch of oxygen all over the place, though in this particular case, it doesn't completely cancel out. Wait, I'm wrong. They actually do completely cancel each other out. And so if we take a look at what we're left with, the things that don't cancel each other out in any way or form, we get this. Surprise! This sort of looks like the equation for the standard enthalpy of formation for butane, doesn't it? And it's lucky that it does because you don't necessarily have to literally find what the standard enthalpy of formation is for every single compound that exists. Mostly because it's not really doable. It's not really doable to take carbon, the solid, and take a bunch of hydrogen gas and make specifically butane. But you can use other information from reactions that we do know about, and because experimentation and things like that, to find out information about other reactions that we don't know as much about without having to do impossible reactions. In terms of the enthalpy for this reaction, you're basically going to take all of these and you're going to add them up. And there you go. That's going to be the enthalpy for this particular reaction. So Hess's law is basically saying it doesn't matter what road you take to get to a particular reaction. As long as your initial and final states of your system are going to be the same, you can add as many reactions as you want, and you will get the enthalpy. The enthalpy works out. Now, when it comes to solving these kinds of questions, my general advice is going to be figure out what your final equation that you want is, see what you have in terms of the thermochemical data that you have, the references that you have, and see what matches up with where you want to get to. And here I'm going to remind you that states are incredibly important. If your states don't match up, you're going to need other data to add in to make sure those states do match up. If you don't have a needed equation, it's not given in the question itself, go and find it from those various references, and then arrange your given equations in a way that they'll add up to the desired equation. So let's take a look at this particular question. We want to find the enthalpy of formation for propane. This is the information that we have. So first off, let's write down what we do have and what we're going to need to find. So at this point, all I've done is written out the balanced chemical equations, or the chemical equations, for what each of these definitions are referring to. Now, let's look at what we need our final equation to be. So it's asking for the enthalpy of formation for propane, so it's for 1 mole of propane from its elements in standard state. So this is the final equation that we need. So now we need to figure out how can we use this to get here. So for this, my recommendation, especially if you're working with something related to combustion, is leave all of the hydrogens and oxygens to the very end. They are usually going to be the most complex and annoying things. So in this particular case, the easiest one to probably deal with first, or to look at first, is going to be our propane, because it only shows up in one of these equations. So if we look at this particular equation, we can see that we do have our propane in our reactants, but we need it in our products. So we basically need to take this equation and reverse it. So we're going to take this and multiply it by -1. So here's what that will look like reversed, and then here is our delta H for this reversed reaction. From here, let's take a look, see what are the things that we need to get rid of or add to make sure we get to our final equation. So we know that first thing, if we look at this, we have carbon dioxide in here. We have no carbon dioxide at all in our final equation. So that means we're going to have carbon dioxide. It's going to need to be in the product so that we can cancel them out. And we need to make sure we have 3 carbon dioxides to make sure they cancel out. So we're going to basically take this equation. You can see that it already has carbon dioxide in the products. We need 3 carbon dioxide, so we're going to take that and multiply it by 3. Now we also still have waters, and we need to get rid of those waters. So again, we're going to look for something that has water on the right. We want to make sure we have water on the right side, or we're going to need 4 of that. Let's take this, and this one will multiply by 4. Now, yes, we have a whole bunch of oxygens, but there are oxygens everywhere. We also have to make sure we have the right number of carbons and hydrogens. But for now, let's see if things cancel out to get to where we want them to be. So our carbon dioxides are going to cancel each other out. None of that is left. Our waters, we also made sure that we were going to be able to cancel them out. And then for our oxygens, well, we have a total of 5 oxygens on this side, and we also do have a total of 5 oxygens on that side. So that means all of our oxygens do cancel out. And hey, looky look, we do have exactly what we want left over. And here we go. Now it is asking for enthalpy of formation, and since we did find it for exactly 1 mole of our propane, you could also say that the delta H in this case, or the delta H naught of propane formation, is negative 105.5 kilojoules per mole, because we did do it for 1 mole of the stuff. So theoretically, everything should cancel out really nicely. If things are not canceling out, a few things to look for are, did you make sure all of your states are correct? Also, did you do the math correctly? Did you make sure you are multiplying things as they should be and you multiplied everything correctly? If those things have worked out, theoretically, things should cancel out beautifully and you should get to where you need to be. Now there is another way of showing this work, and that's referred to as an enthalpy cycle diagram. So you can also draw this as a diagram and show your work that way. So let's look at the same reaction that we were looking at before and take that and draw it as an enthalpy cycle diagram. So at the end of the day, this was the reaction we wanted to get to. This is what is referred to the direct path. Now, if you think about the other reactions, those other reference values that we were using to get to that direct path, all of them ended up being associated with carbon dioxide and water. So we had the combustion for that one, and then we had the enthalpies of formation for the carbon dioxide, linking these two to our left. And then here are those enthalpy values along with the modifications we needed to get to the numbers that we needed. Now you can see here that I am leaving this one as negative because the information that we're given is taking the propane and burning it. So these are our reactants in the information that we were given, and those are the products. Now another thing to note is that we did not add any oxygens in here. Oxygens usually do get canceled out or get taken care of, and so a lot of the times you don't include the information about the oxygens. Sometimes you might also see oxygens being added in, so you add them in here, add them in there, and then they do get taken care of, but you don't have to worry too much about oxygens. Now, if we are going to go from here to there, using our indirect path, we would be going that way. So when we are going from there to there, excluding all the oxygens, you will see that things will cancel out. And when you're calculating the delta H for this, we are following these in the same direction as we were given. But for this last value, we are going in the opposite direction. So we are going to take that into consideration by, instead of adding them, subtracting it. And this will give you the same value as we got in the last time. Now, if you are an IB student, the IB is going to expect you to know how to use an enthalpy cycle diagram. If you're not, then it's up to you. If you feel that this is useful, then go ahead and use it. If it's not, then don't. That's the end of this lesson. I'll see you next time.